Hi, this is Eigenvalues Part 2, the second part on the lecture on eigenvalues and eigenvectors. Um, some of these new um, definitions are going to be ultimately used for factorizing or writing a matrix as a factorization, which involves the product of three matrices. And the eigenvalues will appear listed in they will appear listed in the matrix that's in the middle. So the definition of eigenvalue and eigenvector involves a vector equation of the form if the given matrix A is a square matrix. So this is the matrix A, and we're comparing that to a vector X. We want to say that this product is equal to that vector X, if you will, scaled by a scalar called lambda, or you can think of that scalar as something that amplifies or shrinks that vector x. That's the way of thinking of a scalar multiple lambda. So this equation here, being a vector equation, is at the center stage in defining eigenvalues and eigenvectors. This is the eigenvalue eigenvector definition, eigenvalue eigenvector problem. And we want to convert that problem into something that looks like A minus lambda times the identity matrix, that being a matrix on its own right that multiplies vector x, and that equals to the 0 vector. This here on the right hand side is a vector that contains a column vector made of zeros, made of n zeros, because we're assuming that this matrix is a square matrix with n columns and rows. So this problem here, if we think now of x, this leads to treatment of this as this is determinant. We're going to consider that as determinant of this matrix A minus lambda I, and we're going to think of this matrix as in terms of the null space of this matrix. This being a homogeneous system, we're thinking on what are the vectors, non-trivial vectors x that solve this homogeneous system. Those would be exactly the vectors that belong to the null space of A minus lambda I. So the eigenvalue problem then relates to the null space of the matrix A minus lambda I. A is the original matrix. So basically, this means that you take the original matrix and subtract lambda from every value on the diagonal of that original matrix. That gives you a new matrix, and we're interested in the null space of that new matrix. But we remember that if the determinant of a matrix is 0, that matrix is singular. So we are checking the equation, this now being a scalar equation that says determinant of this matrix being equal 0. That would imply singularity on the matrix A minus lambda I. So the way this looks in practice, we've made some of these comments before. So the way this looks in practice is as follows. So let's revisit this example. So we have a matrix here is 2 by 2, and so currently our current goal is to calculate eigenvalues lambda. Okay, and so here is this matrix in this example. It's a 2 by 2 matrix, and there is some blank space here, and so we want to know what are the eigenvalues, right? This is what we want, the eigenvalues of these 2 by 2. Well, those eigenvalues, and the answer is eigenvalues are -1 and 5, right? But why? Okay, that's what we want to see next. So determining that these are the eigenvalues is something that comes from the definition of eigenvalues and eigenvectors, which is this vector equation. The matrix multiplied by a non-trivial vector x equals lambda times identity times x, and that is translated into, this is the identity of the 2 by 2 identity. So I2 is the 2 by 2 matrix that contains 1, 0 in the first column and 0, 1 in the second column. Okay, so this would be considered I sub 2. That's the 2 by 2 identity. So even though we're interested on lambda, for which this vector equation is true, by exploring the null space of A minus lambda I, specifically by making use of the fact that if the matrix is singular, the determinant is 0. So we say, well, consider the determinant of A minus lambda I equal to 0. And this will be consider the determinant of A minus lambda times I. Okay. And so this becomes A minus lambda I is this matrix here. This matrix is 2 by 2, and that is A minus lambda I, which is basically take the original matrix and subtract lambda from the diagonal entries. You're still operating with a 2 by 2 matrix. We're subtracting lambda from the diagonal entries, but now this whole thing is a scalar equation, okay? Because the determinant is an operator. Just remember, the determinant is an operator. The input of this operator is a matrix. The output of that operator is a scalar. So we compute the determinant of a matrix, and that is on its own a scalar. And the determinant of this matrix involves multiplying the diagonal entries and subtracting. So here we multiply -1 minus lambda times 5 minus lambda, and subtract 0 times 2, that is 0, right? So we come up with this expression, minus 1 minus lambda, 5 minus lambda, and so what happens at this step here is that, remember, all these left-hand sides, we carry out, right? We start with 0 equals determinant. We're working our way through the right side of that first expression, right? And now we arrive at the expression 0 equals this product here, right? 0 equals to that product. So what happens if we multiply both sides by -1? We multiply both sides by -1. We obtain this, and from that expression, so maybe some little bit more of arithmetic or algebra we need to do here. So from this expression, we have 0 equals lambda 1 times quantity lambda minus 5, right? And from this expression, we say, this is true if and only if lambda plus 1 equals 0, or lambda minus 5 equals 0. So from lambda plus 1 equals 0, we say that is true if and only if lambda equals -1. And then from this expression, we say lambda minus 5 equals 0 if and only if lambda equals 5. So we find two potential values here that solve these equations, and these values are precisely the value of -1 and 5. And these are the reasons. Okay, that's how we arrive at specific values of lambda. We started by assuming that 0 is equal to the determinant of A minus lambda I. This is a direct connection to the definition of singularity. If the matrix A minus lambda I is singular, then the determinant of that matrix is 0. And being singular means that there are non-trivial vectors for which being singular means that the null space of A minus lambda I will contain non-trivial vectors that solve the equation A minus lambda I multiplied by that vector equals 0. So now that we made use of this scalar equation to find values of lambda, we could do something else. We could find values. We could find eigenvectors, but let me pause here for just a second. So to be a little more formal, before we compute vectors associated to specific values of these specific so-called eigenvalues, to be a little bit more formal, so let's have some notion of let's introduce the definition. And this definition is going to involve a polynomial, and this polynomial is defined, okay, with this determinant of a matrix minus scalar times identity. So let's just consider this scalar. We were using lambda before, but let's use a different character here. Let's use t, for example. And I mean, you could note that in the previous example, we end up with an expression that was involving lambda in a way in which this was factorized, right? This, if we were going to multiply this out, so this would be lambda times lambda, lambda square, and then we'd have minus 5 lambda, and then plus 1 lambda minus 5. So this would give a quadratic polynomial in lambda. And so there is a general definition of a polynomial obtained by computing a new matrix A minus whatever symbol you want to use for that variable. I'm choosing here the symbol t as in time, A minus ti, and then computing the determinant of that new matrix A minus ti. That determinant, this determinant, is a scalar. This is a complex number, but that scalar is in fact an expression that is a polynomial here to be denoted here, to be dubbed from here on, from here forward, to be known as characteristic polynomial. Okay, so that characteristic polynomial will have a very important role because the roots of that characteristic polynomial are the so-called eigenvalues of a matrix. So the first step in finding eigenvalues will be in determining what is the polynomial at hand, the polynomial to be used, and then we will proceed to compute the roots, the values at which that polynomial is equal to 0. So for an eigenvalue lambda associated with a non-trivial eigenvector x, we would say that x is a non-trivial member of the null space of A minus lambda I, and the matrix A minus lambda I will be singular and will have a 0 determinant. So in other words, we are using that we depart from the eigenvalue eigenvector equation. We know that is true if and only if this is still a vector equation of the form ax minus lambda I x. We can express this as a homogeneous system where the matrix of coefficients here is a minus lambda I, quantity a minus lambda I multiplying the non-trivial vector x, and that is equal to the 0 vector. That is, if x is unknown, this is a homogeneous system of equations. And then we could express, for a minute, think of a minus scalar times I. So let's denote that scalar as with the letter t. Think of now the determinant of a minus ti equal to 0. And that expression, this is the part where we're interested. These are the solutions of these are the so-called roots of the polynomial in t, here denoted as p sub a of t. Roots are values at which that polynomial equals 0. So if we have a square matrix A, the lambda is called an eigenvalue of that matrix A if and only if lambda is a root of the characteristic polynomial of that matrix. In other words, if the characteristic polynomial is evaluated at that value of lambda, that polynomial takes on the value of 0. That polynomial vanishes, or when evaluated at this eigenvalue, the polynomial, the characteristic polynomial, equals 0. Okay, so that's a definition. Well, that's a theorem here. We're learning this is a theorem that we would like to exploit, because when we are computing eigenvalues, we will take the matrix, compute the characteristic polynomial of that matrix, and then proceed to compute the roots of the characteristic polynomial of that given matrix.